Density function is nothing but we denote it as small fx of x, okay, and density function is derivative of distribution function. So small fx of x is dfx of x by dx, okay, so it is derivative of distribution function. This density function we call it as pdf, probability density function, pdf, okay. So when this density function will exist, we know that the derivative of distribution function is the density function, no? Whenever the derivative of distribution function exists, then the density function will exist, okay. So in some places where we will not be getting the derivative of distribution function, for example, you take this continuous random variable, okay, it will be having continuous distribution function fx of x as shown in the figure, okay. At these locations it will be discontinuous, okay. So here the slope will change suddenly at these places, okay. So finding the derivative at these places are difficult. That is why whenever we have continuous distribution function, the continuous distribution function will be summarized by the step waveform, okay. Whenever we have this type of waveform, okay, if you take the derivative differentiation, okay, of a continuous random variable, we will be getting the density function like this. This is the distribution function. The first figure is the distribution function. Derivative of this figure is nothing but the density function, okay. So whenever we are finding the density function, we have to take care that the area under the density function will be always equal to 1, okay. So and for discrete random variable, we have discussed that the discrete distribution function will be having stage step waveform, okay. So to define the derivative of that, because what is density function? Density function is derivative of distribution function. To define the derivative of that, what is that we use here? We use the impulse function, okay. One of the most important properties of impulse function here is uh, here is that if you want to find out the function value at x is equal to x naught, what do you have to do? We have to multiply integral minus infinity to plus infinity phi of x del of x minus x naught dx will be equal to what? Phi of x naught. This is one of the important properties of impulse function, so that we can obtain the function value at x is equal to x naught, okay. So what is impulse function? Impulse function will be having zero duration and amplitude will be equal to 1. See infinity. The amplitude will be, it is having zero duration and amplitude will be equal to infinity. So the total area under the impulse signal will be always equal to 1. Okay, so we'll also obtain what is the relation between function and the step function. So del of x is the impulse function. It is given as derivative of step function. Okay. So del of x is equal to du of x by dx. And the vice versa relation is here is integral minus infinity to x del of psi d psi is equal to u of x. Okay. So these two gives us the relation between impulse function and the step function, okay. So we have discussed that the discrete random variable gives us discrete distribution function. So what is that here? What is the discrete distribution function? It is given as fx of x is equal to summation I is equal to 1 to n p of xi u of x minus xi. This is the distribution function, okay. Now what is density function? Density function is derivative of distribution function. So fx of x is equal to dfx of x by dx, okay. And just now we have discussed that we have derivative of step function. What is the derivative of step function? Is impulse function. So from capital fx of x we will be getting small fx of x is equal to summation I is equal to 1 to n p of xi del of x minus xi. So this is the example we have discussed in the previous example. So this is the state step waveform. What is this? This is the cumulative distribution function. Okay. Now if you apply derivative to this, what is that we get? We get the density function. How will be the density function? Wherever we have there is a rise in the step. Okay. At that location, we will be getting the impulses. Okay. So we will be getting impulse at -1, -0.5, 0.7, 1.5 and 3. So what is the height of this impulse? How much the signal is raised? So here if you observe, the signal is raised by zero point 0.2, here it is raised by zero point 0.1, here it is raised by 0.4 and here it is raised by 0.2. So here how much it is raised? That will be the amplitude of impulse signal. Okay. So like that we will be getting the density function from the distribution function, whereas the distribution function will be having state step waveform, whereas density function will be having the impulses at the corresponding locations where the step is occurred. Okay. And the amplitude of impulse will be equal to the amplitude of step signal. Okay. And now we'll discuss what are the properties of density function. The first property says that the density function will be always non-negative. That is, fx of x value will be always greater than or equal to 0. Okay. And the second property is that the area under the density function should be always equal to 1. That is, integral minus infinity to plus infinity, fx of x dx value will be always equal to 1. Okay. And the third property says that the distribution function, capital F is nothing but the distribution function. Capital Fx of x is equal to integral minus infinity to small x fx of psi d psi. Okay. So you can obtain the distribution function from the density function. So integral of density function is nothing but the distribution function. And fourth property says that if you want to find out the probability between x1 and x2, that is probability of x1 less than x less than or equal to x2 will be equal to integral x1 to x2 fx of x dx. Okay. So these are the four properties of density function. So now we'll see the proofs of this property. The first proof is fx of x will be always greater than or equal to 0. So fx of x is always positive. It is non-negative number. So we just know that what is density function? The density function is nothing but the derivative of distribution function. And just now we have discussed that what is distribution function? Distribution function is always monotonically increasing function. It will increase. That is, fx of x1 will be always less than or equal to fx of x2 if x1 is less than x2. Okay. So fx of x is monotonically increasing function. So if it is increasing function, what is the derivative of increasing function? Will be always positive. That is why fx of x is always negative. Okay. And the second property says that the area under the density function will be always equal to 1. Okay. Now we know that what is fx of x? Fx of x is derivative of distribution function. Capital F is distribution function, small f is the density function. Fx of x is the derivative of distribution function. Now we integrate both sides of this equation with respect to x. So if you integrate with the limits minus infinity to plus infinity, what do you have here on the right side? We have the integral minus infinity to plus infinity dfx of x. Okay. Now we will be getting fx of x and substitute the limits minus infinity to plus infinity. So we get fx of infinity minus fx of minus infinity. And from the properties of distribution function, we know that fx of infinity is equal to 1, fx of minus infinity is equal to 0. So this value, what is that? We get integral minus infinity to plus infinity. Fx of x dx value will be always equal to 1. Okay. And the third property says that fx of x, what is the distribution function? The distribution function is integral of derivative function. So integral limits are minus infinity to x fx of v dv. Okay. Now How do you find out cumulative distribution function? Cumulative distribution function is integral of probability density function. Okay, so fx of x is equal to d by dx of fx of x. Okay, so now we integrate both sides of this equation. If we integrate this, we get integral minus infinity to x fx of x dx. It is equal to integral minus infinity to x d by dx of fx of x. Okay, so d by dx of fx of x dx will give us fx of x only. Now substitute the limits minus infinity to x. Okay, so if you substitute the limits, then we get fx of x minus fx of minus infinity. And from the properties of distribution function, we know that what is fx of minus infinity? Fx of minus infinity will be equal to 0. So from this we know that what is fx of x? Fx of x is equal to integral minus infinity to x fx of x dx. Okay, this is our third property. Now we'll see the fourth property. What is the fourth property? The probability of x1 less than x less than or equal to x2 can be obtained from the density function, that is integral x1 to x2 fx of x. Okay, and we have already discussed what are the properties of distribution function. From the properties of distribution function, we know that probability of x1 less than x less than or equal to x2 will be equal to fx of x2 minus fx of x1. This relation we got from the properties of distribution function. Okay, so and we know what is that fx of x2, fx of x2 ma. In the place of x, what you have? X2. Fx of x2 is equal to what? It is integral minus infinity to x2 fx of x dx. Okay, similarly fx of x1, from the property 3 we know that fx of x1 will be equal to integral minus infinity to x1 fx of x dx. Okay, now see here what is x2. X2 value will be always greater than x1. See this here on the scale I have mentioned. This scale is from minus infinity to x2. So x1 is bit less than x2. So minus infinity to x1 and x2 we have. Okay, so integral minus infinity to x2, integral minus infinity to x2 we divide into two parts, that is integral minus infinity to x1, then from x1 to x2. So integral minus infinity to x1 fx of x dx plus integral x1 to x2 fx of x dx minus integral minus infinity to x1 fx of x dx. So in this two integrals will get cancelled because the limits of integration and the function is same. So the limits of integration is minus infinity to x1 fx of x dx. Okay, so the function is also same. These two integrations will get cancelled, so we left with integral x1 to x2 fx of x dx. Yes or no? So from this, the probability of x1 less than x less than or equal to x2 will be equal to integral x1 to x2 fx of x dx. Okay, so if you have any function, you want to check whether that function is density function or not. What are the two properties we need to check is the first one. What is the first property? What is the first property of density function? The density function is non-negative number, and the second property says that the area under density function will be always equal to 1. Okay, so these two properties we use to check any function to be a valid probability density function or not. Okay, if these two tests are satisfied, then we say that that particular function is valid a density function. Otherwise, we say that it is not valid density function.